I would like to talk about multi-phase reconfigurable LLC resonant converter with passive current balancing and wide voltage gain range. The proposed converter achieves capacitive current balancing capability. Since both the primary and secondary side circuits are reconfigurable, the voltage gain range is extended. Furthermore, the proposed converter can double the voltage gain range compared to conventional converter. The experimental verification using a 1 kW prototype demonstrated passive current balancing and extended voltage gain range. Here is the outline of my presentation. First, let me explain the onboard battery charger and conventional reconfigurable LLC converters. After that, I'll propose a multi-phase reconfigurable LLC converter and describe the detailed major features. Finally, let me show experimental results using the 1 kW prototype. I'll start by giving an overview of onboard battery chargers. This figure shows an ordinary battery charger system in electric vehicles. To extend cruising distances, vigorous development on high-capacity lithium-ion batteries has been underway. In general, the voltage of batteries varies in the range of 100 to 420 volts depending on the state of charge. Therefore, onboard battery chargers require isolated DC-DC converters with a large current capacity and wide voltage gain range of 0.25 to 1.05. Here, you can see interleaved converter, which is adapted as isolated DC-DC converters for large current applications. Interleaved converters consist of parallel connected converters so that they can increase current capacities. In addition, current ripples of the input or output ports can be reduced by operating out of phase at the same frequency. However, phase currents of parallel connected converters are unavoidably imbalanced because of component tolerance, resulting in current concentration. That's why interleaved converters require current balancing capability. Meanwhile, LLC converters are widely used in isolated applications thanks to their features of high efficiency and power density. In general, the output voltage in ordinary LLC converters is regulated by pulse frequency modulation control, because these gain characteristics are depending on switching frequency. To balance phase currents in multi-phase LLC converters, switching frequencies must be individually adjusted. In other words, interleaving operations cannot be simply applied to LLC converters. Additionally, ordinary LLC converters operate close to the resonant frequency to achieve high efficiency. However, LLC converters require a wide switching frequency range to extend the voltage gain characteristic. In the next slide, I'll show active current balancing techniques for interleaved LLC converters. As you can see, these are interleaved LLC converters with current balancing control. These converters can adjust resonant frequencies for current balance by adding components such as a variable inductor and numerous switches. However, these active current balancing techniques eventually need additional feedback control loops and current sensors, resulting in increased complexity and cost. Here, the multi-phase LLC converter with not only extended voltage gain range but also passive current balancing capability thanks to charge conservation of flying capacitors. The primary side circuit is reconfigured between a full bridge or half bridge inverter and the second side one between a double or full bridge rectifier. The detailed principle is similar to a proposed converter, so I'll explain it later. In the next slide, I'd like to propose a multi-phase LLC resonant converter doubling the voltage gain range compared to this conventional topology. Three-phase topology comprises 6 switching legs, 3 LLC resonant tanks, and 2 flank capacitors. 2 flank capacitors are added to the right-hand legs in phases A and B. Secondary side switches replace the diode in part of the full bridge rectifier. Similar to ordinary LLC converters, output voltage is regulated by pulse frequency modulation control. 3 phases are driven 180 degrees out of phase. In other words, phases A and C synchronize, whereas phase B lags 180 degrees. On the primary side circuit, high and low side switches operate in a complementary manner with duty equal to 0.5. In the proposed converter, the number of phases can be arbitrarily extended. This figure shows a 4-phase topology. Phases A and C synchronize, while phases B and D operate 180 degrees out of phase. The current capacities in the proposed converters can be enhanced by extending the number of phases. Next, I will discuss circuit configuration on the primary side. The transformer's primary side circuit operates as either a full bridge or a half bridge inverter. All legs in the full bridge inverter are driven. In the half bridge inverter, high and low side switches in the left-hand side legs are always off and on, respectively, and right-hand side legs are driven. Meanwhile, the secondary side circuit operates as either a double or a full bridge rectifier. Switches are always on in the double configuration, while switches are always off in the full bridge rectifier configuration. In summary, the proposed converter operates in 1 out of 4 configurations, which are full bridge double, half bridge double, full bridge rectifier, and half bridge full bridge rectifier. Next, I describe the current balancing mechanism in full bridge configuration. These figures show theoretical key waveforms and current flow direction in mode 1. VQA to VQC are drain source voltages of switches, and IA to IC are the phase currents in phases A to C respectively. Focusing on flank capacitors, CA is charged by IA and stores QA. On the other hand, IC discharges CV and CV releases QC. During mode 2, CA is discharged by IB and releases QB. At the same time, QB is stored in CB by IB. In summary, thanks to the charge conservation of 2 flank capacitors, QA equal QB and QB equal QC, all phase currents can be passively balanced. In the half-bridge configuration, all phase currents are passively balanced on the same principle. This slide describes the derivation of gain characteristics. The proposed converter consists of parallel connected phases, while voltages of resonant tanks among phases are equal in the half-bridge or full-bridge configuration, respectively. The proposed converter is converted into this equivalent circuit. By applying the fundamental harmonic approximation, Fourier transformed equivalent circuit can be yielded. Consequently, the voltage gain of half-bridge full-bridge rectifier is yielded as follows by Fourier series. According to this analysis, compared with the gain of half-bridge full-bridge rectifier, half-bridge doubler, full-bridge rectifier, and full-bridge doubler are 2, 4, and 8 times higher. In addition, because VM tank is double compared with the conventional one, gain characteristics in the full-bridge configuration are twice than conventional converter. These figures show that comparison of voltage gain characteristics. As you can see, gain characteristics in the full-bridge configuration are doubled. Combining two figures, appropriately changing the circuit configuration allows a higher voltage gain range without changing the switching frequency operating region. Finally, let me explain the experimental verification. This figure shows photograph of the 1 kW prototype. In order to verify the passive current balancing, key parameters of transformers were intentionally mismatched. These figures show measured phase current waveforms in full-bridge and half-bridge configurations at 130 kHz and input voltages equal to 200 volts. Charge amounts of flying capacitors in phases A to C were equal, with errors less than 4% in both configurations, despite mismatched transformers parameters. Phase currents were passively balanced. Next, I'll explain results of the gain characteristics. 4 configurations were changed, and switching frequency was manipulated in the range of 80 to 170 kHz. This figure depicts gain characteristics in 4 configurations. Y-axis is gain, and X-axis is normalized frequency. Thanks to the reconfigurable circuits, the gain range was extended. In addition, the proposed converter covered the gain range of 0.25 to 1.05. In conclusion, I have proposed the multi-phase reconfigurable LLC resonant converter. Thanks to the charge conservation of flying capacitors, phase currents can be passively balanced regardless of circuit configurations. Additionally, the proposed converter can double the voltage gain characteristics compared to conventional converter. I introduced experimental results using a 1 kW prototype. These results demonstrated widened the voltage gain range and passive current balancing in both full-bridge and half-bridge configurations. Thank you for your attention.